We have seen a simplex method for solving linear rational arithmetic constraints, and to complete the conversation we will look at some other methods that were proposed in the past for solving linear rational arithmetic constraints. Some of them are as good as simplex, and in various contexts and various areas where we want to solve linear rational constraints. So we have been seeing the success of SMT solver and their algorithms. Today we'll look at methods that may look efficient on paper but do not perform very well in the context of SMT solvers. Furthermore, this lecture is more about the understanding that we are using simplex to solve constraints. That is not the best idea out there. Maybe the other methods or some variants of those methods are better than the current design of the SMT solvers, and jury is still out what will be the best design. So today we will look at four such methods. One is Fourier-Motzkin and ellipsoid method in particular. These two methods were proposed in the past and later on improved further, and now the most of the tools implement is some version of material points method or Konmaker's method. But today we will focus just for understanding these two methods in particular. So let's look at Fourier-Motzkin. A method cannot be simpler than this method. So what it does is follows. Okay, the algorithm proceeds by eliminating variables one by one. After elimination, all the variables, if the input is true, then the input is satisfiable, otherwise is unsatisfiable. So let's see how it works. Let's suppose I have constraints ax less than equal to b, and you can write it down into three different conjunctions. Okay, one in which you can take a variable x and write it like x is greater than equal to sj expression, and in other setting in those constraints where x can be written down as x is less than equal to ti, you can put them in a separate set, and where x does not occur you put them separately. So now you know that x should always be bigger than all sj's, and you also know that x should be less than equal to all ti's. So we can eliminate x from this constraint system. How do we do that? Simply take the all combination of sj and ti and say the sj is less than equal to ti. If that is the case, then if these constraints are true, then you can always choose an x such that these constraints hold, and other way around. So if you look at these constraints, you may wonder how would you support strict inequality, strict equality, disequalities, and the inequalities. Please think about it, how to solve those constraints. This method is very inefficient because each time you have a quadratic blow up. You can see that this is there are m constraints, there are l constraints, and here is you have n constraints, and at the end you will get m times n l constraints plus n, and this is a quadratic blow up, and we don't like such quadratic blow up at each step because it will at the end when we eliminate some number of variables, it become very large and actually as an exponential blow up. So therefore this method is not implemented in practice. This method is not only bad in theoretical sense but also in a practical sense. In practical settings, this Fourier-Motzkin procedure tend to expose the constraints to very large constraints. So let's look at an example and try to understand how it works. So consider this input constraints. You have three variables x1, x2, x3 occurring in various ways. Let's choose x1 first and try to eliminate it. So wherever x1 is appearing as a negative coefficient, we will move it other direction, and if x1 appears as a positive coefficient, then we'll move everything else other direction. So if you do that, so you will get x in from the first constraint, I will get the lower bound for x1. From the other two constraints, what do we do? X1 stays here and everybody else moves on the direction. Then we get x1 is less than equal to x2 and x1 is less than equal to x3. And the last constraint, you can see that x1 does not occur, so we don't care about it. Now how do I eliminate x1? For every lower bound, we say it should be smaller than the upper bound. Okay? And we state that. So we get that every lower bound is smaller than every upper bound. And we got this elimination process. Now we can further go ahead and try to eliminate another variable. Before that, we will try to simplify these constraints, and we find these constraints. Now what we do, now we can eliminate x2 because there is no lower bound for x2. x2 occurs in only one constraint, so therefore there is no other bound for x2. So you can just simply drop the atom where x2 occurs. You can simply see that you can choose the value of x3, and based on, and if you want to satisfy x2, you can just arbitrarily choose the value of x2 depending on x3. There is no constraints to be solved for value choosing value of x2. After that, we are left with these constraints. Now we try to eliminate x3, and we are left with this constraint: 1 is less than or equal to 0. This is impossibility, therefore original constraint is unsatisfied. So how you think about it? Remember that in simplex we were having this thing that each time we have unsatisfiability, we have something called lambda, which can give us the proof of unsatisfiability. How do we produce the proof of unsatisfiability in this context? And that would be a very interesting exercise to do. So for both complexity and practical performance of the algorithms are bad. Neither it works in theory nor it works in practice, and nobody implements this. But maybe it can be used in a pre-processing phase when there are a lot of lower bounds on x and very few upper bounds on x. Then you can do this operation. But however, since we usually use these constraints as incremental simplex, and we don't see the whole constraint system at the same time, we don't have any idea that how many upper bounds and lower bounds will come in the future, so we cannot really implement this Fourier-Marsden method in practice.